The third page of this published, peer-reviewed scientific journal performed by an accredited university again states the flame speed of hydrogen is 9 times faster than the flame speed of diesel. This is a claim that I have been making and a statement that I have been making ever since I first started endorsing the use of HHO boosting and building boosters and informing the public of the viability of this technology. It goes on to say, therefore, burning diesel in the presence of hydrogen will result in overall faster and more complete combustion. Again, a statement published in a peer-reviewed scientific journal, not a statement made by the one and only Smack. If you look at the top of the page, you will see the experimental setup block diagram, which clearly explains how the system was arranged. Below that, for the different kilowatt load ratings, you see 2 graphs. One is a variation of brake thermal efficiency with H2O2 percentage, and it goes from 0% to 7%. You can see the delta in efficiency as the amount of hydrogen is increased. Same thing on the right hand side, figure 3, except you're using flow rate instead of percentage, from 0 to 35 liters per minute. Now notice the 35 liters per minute is a lot of gas. Most of the designs that are out there that are being built, replicated, sold are not over 10 liters a minute. As a matter of fact, the average is about 2 liters a minute. But even so, on the graph between 0 and 5 liters per minute, you can see a very definite increase in percentage between those two flow rates. These 2 graphs clearly demonstrate that the addition of hydrogen and oxygen increases the brake thermal efficiency of this particular diesel application. And the page goes on to discuss, now this is very important, discuss tuning aspects, for example, port injection timing, okay, of that particular diesel engine. I bring attention to this fact because I want to reiterate the importance of tuning your specific application to the percentage of fuel used. If you're using HHO injection, you need to specifically tune your engine for the presence of that gas. I cannot emphasize that fact enough. And I have proven that. In my genset, my own personal genset tests that I ran, I proved that tuning was necessary. Adjusting the air-fuel ratio mixture was necessary. And I didn't even go into adjusting the timing. These guys adjusted timing to further increase, which would indicate a reason why every application may exhibit different percentages in increase. You may look at the graph and say, well, it took 10 liters a minute just to get a simple, couple percent increase in mileage. And that is because of the tuning. Tuning must be properly done. So again, I cannot emphasize enough the importance of proper tuning. That is why many times when people try to implement HHO technology on their vehicles, they may not see a gain or they may see a decrease in mileage. Without proper tuning, as I've demonstrated very clearly, the HHO injection method does not work. And that was seen in the EletrikRide tests, combined with bad cell technology. When you design a cell that doesn't hold up, that falls apart, and you don't do proper tuning, you will not see results. Now, page 4 of this published scientific investigation on HHO technologies states very clearly, the figure reveals, and that's referring to figure 4 at the middle of the page, that the addition of a small amount of hydrogen-oxygen into the air intake to enhance diesel combustion decreases the brake-specific fuel consumption regardless of the level of the load. And in figure 4, you see 3 different load rates of 19 kilowatts, 22 kilowatts, 28 kilowatts. Each curve in brake-specific fuel consumption decreases. Figure 5, which shows the variation of total fuel flow rate with hydrogen-oxygen percentage, also shows a very prominent decrease in flow rate. Again, this is a scientific, published, peer-reviewed paper done by an accredited university. Figure 6 shows variation of fuel saving with hydrogen-oxygen percentage. In percentages, for each load rate, the observer can clearly see the increase in fuel savings as the hydrogen-oxygen percentage increases. Notice, at about 5% in figure 6, the line seems to level off. This, according to the paper, indicates that beyond 5% induction, H2O2 mixture acts as a fuel rather than an additive. Yes, HHO is a fuel, and the more you add, the more you must tune, because the more it begins to overtake the role as a primary fuel source for the engine. Scientific paper, peer-reviewed, published by an accredited university. Figure 7 shows and correlates the data that I showed with my own generator tests. Variation of air-fuel ratio with equivalent hydrogen-oxygen percentages. As the percentage of HHO increases for every power range, you see a definite increase in air-fuel ratio. Scientific public paper, published, peer-reviewed, accredited university. Second to last page, we discuss the emissions. Clearly being shown, at 19 kilowatts, the hydrocarbon emissions drop from 187 ppm to 85 ppm with 31.75 liters per minute induction of hydrogen and oxygen. At 22 kilowatts and 28 kilowatts, the hydrocarbons emissions decreased from 189 ppm to 93 ppm by adding 29.84 liter per minute, and from 192 parts per million to 97 parts per million by adding 30.6 liters a minute of hydrogen and oxygen respectively. Again, these flow rates of hydrogen and oxygen are very high. Most cells are not producing that much gas, which would explain why the percentages are much smaller than published in this paper. For example, my device has never gone above a 20% reduction in fuel consumption, also done on small gasoline engines. You cannot apply the same percentage numbers on all engines ever made, burning on any different kinds of fuels. You're talking about apples and oranges. So one device on one engine will not perform the same as the same device on another engine. This is just common sense scientific principles we're talking about. You cannot expect to put a 2 liter per minute hydrogen generator on a big diesel engine and a 2 liter per minute hydrogen engine on a small gasoline engine and expect to see the same exact results. It is irrational to assume that all percentages are going to be equal across the board on every application. Specific tuning must be done, and the cell output should be designed for the engine that is going to be applied to.